Okay. Hi. All right, let's start. So we're still doing absolute value functions. We're going to talk about when I would use an absolute value in real life. Like what kind of situation or what kind of math problem would I ever graph and my result would be an absolute value. So we're going to do some word problems and then we're going to talk about rate of change. So first off, let's talk about number one. Can I have a volunteer read number one for me? Go ahead. Perfect. All right, so what's happening is a kid is riding in a boat from his house to his friend's house. So they live on a lake. And we need to kind of talk about what's going on here because the borderline is Arizona and Utah. And so Jay drives his boat and he hits the state line and then he goes to Utah. And he continues driving to his friend's house. Now, let's look at this picture graph. This right here, if this is 5, 10, 15, 20, 25, 30, 35, 40, 45, 0, 45 is going to be my y-intercept. The graph decreases. The graph decreases. So time is going by. Half an hour, 1 hour. An hour and a half, 2 hours, 2.5 hours. He's driving in the boat. And as he drives, he gets closer and closer to 0, 45, 30. So like 0.530, that right there would be after half an hour, he's 30 miles from the state line. So ordered pairs along this line show as he goes, he's approaching the state line. The state line is this V, is the vertex of my V. And this means vertex 1.5, 0. That means that it takes him an hour and a half, 1.5 hours to get to the state line. And let me put that a little higher actually. Over 1.5 up 0. That's the x-intercept. So now let's talk about what all these other numbers mean. D of t equals 30 times the absolute value of t minus 1.5. Okay, what does the 30 represent in this situation? They're talking about the 30 in my equation up here. This 30 is going to be J's speed. J's speed. 30 miles per hour. Okay. What does the 1.5 represent? 1.5 miles to get to the state line, and then he starts heading to his friend's house. So it's the downward we'll say is him still driving to the state line. And then he gets to the state line after an hour and a half. And then he keeps driving. And after 3 hours, he gets to his friend's house. So look, these lines are the same. His friend and him live the same distance apart from the state line. But let's still answer B. What does the 1.5 represent? The 1.5 represents his time traveled to state line. His time traveled to the state line. What does the y-intercept of 45 represent? What's 45 mean, guys? Because it's on the distance axis. 45 what? Yeah? Yeah, well, he has to travel 45 miles to get to the state line. So where does he live? How far does he live from the state line? 45 miles. He lives 45 miles. We have to write small, huh? From the state line. How far does Jay travel to visit his friends? So he goes to the state line. His state line is 45 miles away. And then after he gets to the state line, he still has to go to his friend's house. Another 45 miles. Someone knew. How many miles total did he drive? 90 miles. 90 total. 45 to get there. And then he hits the state line. And then it's another 45 to his friend's house. Okay. What's the domain and range of this function? That means if, still the thing, guys, the domain is here from 0 to 3 hours. 0 to 3 hours. So I can say that my domain is between domain. Zero and 3. And I'm putting brackets because it starts at 0 minutes and it ends at 3 hours. All right. Then range. Remember range, I go low to high. So I start low. No negative. There's no negative time. There's no negative distance. No. But it's here all the way to what? What's the top point that I reach, that I top out at? So I start at 0. 5, 10, 15, 20, 25, 30, 35, 40, 45. I stop. My range is between 0. 0 is neither, well, it's a closed circle at 0, so I could do that. And 45. Brackets because it's included, closed circles. So all we're doing with this problem was interpreting. What does each thing mean? Because that's hard enough, right? There's nothing for us to solve for. He traveled 90 miles. He was going 30 miles an hour. Okay? Let's now talk about rate of change. Rate of change is the slope, the rise and run of a line. We will look at a certain section of the line. So I'm going to give you a little boundary line. And I'm going to calculate the rate of change between that boundary line. Here's my boundary line. Between 2 and 2.5. Between 2 and 2.5. So I need you to count the boxes. Start at the low point and rise and run to get to the other dot. Tell me the slope to the other dots, just to this dot. Rise and run, dot to dot. Order pair to order pair. Rise over run. You've already helped. New people. Between 2 and 2.5, what's my rate of change? What's my rise over run? Rise how many, run how many? Yeah.
Rise 3.
1. Now, 3 boxes, okay. And how many boxes did I run?
2.
2 boxes. Now let's talk about what each box represents. If the box is going upward, are miles. Isn't this 5, 10, 15, 20, 25, 30? I'm going to start at 15, and I'm going 15, 20, 25, 30. How many spaces is it from 15 miles to 30 miles? 15 miles. Every box is 5 miles. So it's going to be 15 And I ran hours. Every box in hours along the bottom is how much? Look at the bottom x-axis. What increments am I going by along the bottom? Every box is what? Look at the x-axis, the flat bottom, time. Every box is how much time? How many minutes? 30 minutes every box? Because 2 boxes is half an hour. Half an hour. Half an hour. So each box is what? 15 minutes? Does that make sense? 15. And there's 4 boxes. 1, 2, 3, 4 to get to an hour. Oh, 15 miles. Okay, check this out. 15 miles and the run is 2 boxes. That's 30 minutes, right? So that means that my slope, I could say, is 1/2, 15 over 30, miles over minutes. Okay. All right, let's turn the page. Let's do another one. Or 0.5. Maybe I should do 0.5 for 30. Actually, I should. Hold on, I got to switch something. 15 divided by 0.5. Sorry, guys. If I'm going to do things by the hour, then it's going to be half an hour. Yeah. 30 minutes is 0.5. 15 divided by 0.5. That would be 30. Okay. Sorry. 30. And that was actually my miles per hour, wasn't it? That was my rate, how fast he was going too. Sorry. I needed to change them both to hour because I'm not going by minutes down here on my time. I'm going by hours. So I need to make my time match up. Okay. Next question. A cyclist competing in a race rides past a water station. Here's the water station. The graph of the function shows a distance of time, the function of time equals 1/3 times the absolute value of time minus 60. Shows her distance from the water station in minutes. So now I'm going by minutes. Assume the graph represents an entire race. Okay. My 20, what does the graph tell you about a race? What does the 20 tell us? 20 means what? Here's my 20. It's my y-intercept. 0, 20. What does that mean? Look at what the margin says on the actual axes. Distance from where? Where is she passing? Yep. So here's the deal. Last problem, the guy Jay drove his boat 45 miles to get to the state line, and then after the state line, he kept driving. This woman rides her bike 20 miles to get to the first water station because she's thirsty after 20 miles. Then she keeps riding 20 more miles. See how they're exactly the same? This is 20 to get to the water station. This is 20 miles to get past the water station. Okay, what else? Her rate is 1/3. 1/3, by the way. Holy moly. 1/3. Oh, it's in kilometers. Oh my gosh. 1/3 a kilometer per hour. That's how fast she drives, or rides her bike, sorry. And the water station takes her 60 minutes to get to. 60. The time in minutes to get to the water station. So by looking at a graph, I can dissect it and I can tell what each thing means. All right. Find the rate of change. Moving on, number 4. Find the rate of change of the following graphs. This means between 0 and 4. That's what the brackets mean. That's what the inequality also means. So I'm going to draw my boundary lines between 0 and 4. And all I care about is the rise and run of that section in between my red. Draw your boundary lines, please. What's the slope, rise over run? What is my line going uphill or downhill between those? Downhill. Okay, now I have to find the slope. And that means that I need to make my own ordered pairs wherever there's a perfect intersection. Part of finding slope means that you need to figure out where is there an ordered pair. Obviously, guess what? There's an ordered pair at 0, 0. And then I'm going to go down in between 0 and 4 and look and see where is there another perfect. Oh my gosh, right, the next box. I only need 2 dots to go rise and run. So rise what? Run what? I'm rising down. Rise how many? Huh? Rise how many and run. Down and to the right. How many? Someone else. How many boxes did I go down from dot to dot? And how many did I go to the right? 1 down. 1 down. And 1 to the right. That means that my rate of change is -1. So rate of change, -1. -1 over 1 is, just -1. Number 5. Between 0 and 7. Well, guys, my graph doesn't go to 7. So here's the deal. I can decide, doesn't the graph kind of move the same? Like, it's not like my line is zigzagging going different. Doesn't my line just go in a fluid, right? So even though 7 would be over here, 5, 6, 7, I can still figure out the rate of change. And I can just take another little piece of it between 0 and 7. So 0 and 7 is right here. But the line's still going to go in the same order because it's linear. So let's just find the slope of this line of the piece that we have. Okay, what is it? Make your own dots. Do you think it's fair to say that we can make a dot at 0, 0? Is that a vertex? Yes. Where else can I make a dot? Where is there a perfect intersection? Tell me when to stop. Look at my finger, watch it trace. Actually, I should do it on the screen with the video. Tell me when to stop when my line hits a perfect intersection. Perfect intersection. Ooh, you guys are so good. Rise 7, run 2. Rise 7, run 2. 7 halves. Okay, number 6, last one. Ooh, between 0 and 0.33. You guys, when you look at the clock, do you see how the clock can be broken up into 3 parts? Between 12 and 4, that's one section, 1/3. Between 4 and 8, that's another section, 2/3. Between 8 and 12, that's another section, 3/3. Let me draw the little clock on the side. So if I say 0.33333, that means 1/3. This is the 4. This is the 8. And this is the 12. Every section is 20 minutes. Yes? Doesn't the clock make 60 minutes? So if I only want to know between 0 and 0.3 of the hour, 0.33 or 1/3 of an hour is 1 box. 0.3, 0.661. So here's my boundary line. Between 0 and 20 minutes. It's a downhill line. That's negative. Rise how many miles? From dot to dot. Dot to dot. What do you guys think this, it's 0.20. That's my y-intercept. What do you think this dot's at? Over 0.3 up what? How many? 5, 10. What do you want to think? What do you think? It's not quite at 15. 5, 10. What? Not 15. Oh, 13? Sure, let's do it. So I can do two methods. I can take my ordered pairs and subtract y2 minus y1 over x2 minus x1 with my two ordered pairs. x1, y1. x2, y2. Or I can just rise and run. Rise down 7, run 0.3. But that's crazy. That's a lot, guys. Ready? y2 minus y1, 13 minus 20. y2 minus y1, 13 take away 20. x2 minus x1, 0.33 minus 0. This is the slope formula that you learned last year. -7 over 0.33. And I can just leave it like that. Okay? So, in our homework tonight, we're going to find the absolute value. You're going to graph again. And I think I'll add another, what's it called? Column at the bottom where you have to find the rate of change. So I can let me stop the video. One B. Okay.